That concludes my little talk on black holes and Big Bangs. But I want to talk a little bit more about some other things, the cosmic microwave background, because this is now getting a lot of airplay. You have a recent report, BICEP 2 telescope in Antarctica. They found Einstein gravitational waves in polarizations of the cosmic microwave background. No, they haven't. They think they have. It's a figment of their imagination. Let's have a look here of a basis of this. This relates to Kirchoff's law. In German, I think it's Kirchoff. Kirchoff? Yeah. Kirchoff's law of thermal radiation. He takes a box, he lines it with graphite. He checks the radiation. After a little while, he waits, and some radiation comes out. Here he gets this nice little, this sort of expression, nice curve. This is called a spectrum of the frequencies that come out of this radiation. And he calls this a black body. Why? Because it's lined with graphite or soot or lamp black. Yeah? And so he gets this thing here. It's lined with graphite, etc., etc. And you get this black body emission spectrum. Now, the cosmic microwave background is alleged to be a black body spectrum at 2.725 Kelvin. That's just a little bit above absolute zero, right? Black body, remind you. Now, Kirchoff made the mistake of thinking that he could make a box like this out of anything. It could be made of silver or mirrors or anything. And he would get, if he waited long enough, he would get a black body spectrum. So he made one out of graphite, yeah, he gets this. He made one out of soot, yeah, he gets this. So he makes one out of something else, a reflector, a very reflecting material. So he makes a box like that out of reflecting material, and he waits. He waits, it goes past lunchtime. He's getting hungry. He says, well, it's getting late, I'm hungry, and there's no radiation like this coming out. I wonder how long I've got to wait. So he skips lunch and he waits till dinner time. He gets there. I'm not lambasting Kirchoff, I'm just illustrating the waiting time. So he waits and waits and waits, but he doesn't get this spectrum. So he scratches his head and thinks, I wonder if I put a little bit of graphite in there, if it will squash up the waiting time. In other words, I wait less. So he takes his little box that's full of all this reflecting material instead of graphite. He puts a bit of charcoal in there, or Planck does. I'm not sure which one of them did. At least one of them did. Certainly Planck did. So they put a bit of charcoal or some graphite in here, and then he waits. All of a sudden, out comes this. He says, look at that. I've got now a black body spectrum. Marvellous. That piece of charcoal I put in there was a catalyst. I don't have to wait so long. What does a catalyst do? It increases or reduces the speed of a chemical reaction, right? So he puts it in there as a catalyst. Instead of waiting past dinner time or 6 months, he waits a few minutes or an hour and he gets a black body spectrum. So he says, this little piece of charcoal, that's a catalyst. No, it's not. As soon as he put the charcoal in there, this is a reflector. But the charcoal is an absorber. The radiation in that box, there's radiation emitted by the charcoal. It bounces off all the walls, they're reflectors. It goes back into the charcoal. That's an emitter and absorber. It emits again. After a little while, the interior of the box is dominated by the charcoal. It is not a catalyst. It produces the radiation. So Kirchoff made a big blunder. That's 150 years ago, in 1860. Right. But all of this time, recently, Professor Pierre-Marie Robitaille of Ohio State University in the United States has proven that Kirchoff's law is false. The radiation that comes out of a cavity also depends on the nature of the material. This is very important for physics. It's at the foundation of quantum mechanics, because when Planck formed an equation for black body radiation, he introduced the quantum of energy. But this does not hold. So quantum mechanics, the foundations of quantum mechanics are in big trouble. Much of physics now has to be rethought because Kirchoff's law is not valid. We see it all hinges on the insertion of a carbon particle. Now, if you take a glass of water and put it in a microwave oven and turn it on, what happens? Right? Does it get hot? Yeah. If you leave it in long enough, does it vaporize? Yes. So I ask you, does the water reflect or absorb the microwaves? It's pretty obvious, isn't it? The water must be absorbing the microwaves. Now we know from physics that a good absorber is a good emitter. That's why carbon and charcoal, graphite, it's a good absorber, it's also a good emitter. So water must also be a good emitter at what? Microwaves. So water absorbs microwaves, we know that from ovens. Anybody who's been in a submarine knows that you can't communicate with microwaves. Why? Because the water absorbs them. You have to use really long radio waves to be able to communicate underwater. Microwaves won't do it because they're attenuated so much in a very short distance underwater. So submariners know this, and anybody who's used a microwave oven knows this. But if you're a cosmologist, you have no idea. Right? They have no idea. Now we look at the Earth. It looks to me there's a lot of water there. And there's a lot of water in the atmosphere too. And all of this water must be emitting microwaves. Right? How does the water emit microwaves? Let's take some molecules, water molecules. It's H2O. These are water molecules. Well, water has a very peculiar character. And one of the things it does, it forms a hydrogen bond. Here's a hydrogen bond with the dots. The hydrogen here, that's bound to this oxygen by a hydroxyl bond, is weakly bound to this one here by a hydrogen bond. So energy that goes into the water can go in here and it can go in there. But this is a really weak bond and this is a very strong bond. So the energy is not distributed evenly. A little bit will go in here because it's such a weak one and a lot will go in there. So the theory, or rather the theorem of equipartition, which is used in physics all over the place, is also false as a direct result of the invalidity of Kirchoff's law. Right? So this is very important. So the mechanism by which water emits is the same kind of way as absorbs. Well, not quite, but the way it can emit is that these are like oscillators. Like if you take two springs, one really stiff and one really weak, and you can put them together and make a straight line, and then you can jiggle them up and down. This soft one will jiggle a lot, and the other one won't jiggle much. It's too strong. So that's the strong part, this one here, and this is this bit here. This can emit, this is the cause of the microwave emissions from water. Now, let's have a look at a raw microwave image of the sky. It's made up of, let's think of transparencies. You know, in the old days, you used to take a transparency and put it on a machine and it would project. We take those transparencies and we lay them all together. We've got the galactic foreground. That's in microwaves. It's noisy. Monopole means it's the mean temperature of the universe, they say. And behind the monopole is the dipole. The dipole signal is a signal that's produced by the motion of the satellite because it's around Earth or something, right? And the Earth is moving around the sun, and the sun is moving around the galaxy, and the galaxy is moving with respect to the local group. These motions produce a dipole signal. This is well known. The galactic foreground, that's emitted by the galaxy. The galaxy is the Milky Way. We're in the Milky Way, and we're trying to look out of the Milky Way, through the guts of the Milky Way, into space. So this is noise. We want to get rid of that. We want to get rid of the dipole, and behind it is multipoles, and it's an infinite series because the model, mathematical model that they use here is what's called spherical harmonics, and it's an infinite series. So this is the first component of the spherical harmonic, this is a second, or rather this is a 0, this is 1, this is 2. You get quadrupole, octopole, hexadecapole, and goes on, right? So we see here that the galactic foreground, that's in what? It's in millikelvin, thousandths of a Kelvin. The monopole signal is supposed to be isotropic. That means it's the same everywhere. Anisotropic means it's different everywhere. Which way you look, what time of the day, it's different. But if it's isotropic, it doesn't matter where you look or what time, it's the same. And the monopole signal, this is supposed to be the temperature of the universe. The dipole signal is anisotropic and it's noise. We want to get rid of that. It's in millikelvin too. The multipoles, the quadrupole, the octopole, the hexadecapole, and all the rest of them up here, they're in microkelvin or smaller even. So that's a millionth of a Kelvin. Now, balloons and rockets were in Earth's atmosphere. Yeah, there's a lot of water up there, and they're close to the water on the Earth. Equipartition, this is a satellite that's launched by NASA to find the monopole, the temperature of the universe, and this DMR, which is to find all these multipoles, anisotropies they call them. And WMAP was another NASA program to find only anisotropies. They can't do any of this other stuff. It can only find out multipoles. And the Planck satellite was to find multipoles, but it could also determine a monopole if they wanted to. Let's have a look at the COBE satellite. Here we see important thing here. Here is FIRIS, the far infrared absolute spectrophotometer to measure the temperature of the universe. Here's the DMR antennae. These are two antennae to define the These are differential microwave radiometers. And here we find a shield. This shield around the instrument. Yeah. Why? To protect it from radiation. You don't want radiation that coming from up here, down here rather than going in here, because it contaminates everything. So we want a shield to block it all. So they put a shield on, but does it block microwaves? No. Their shield does not block microwaves. It could never do that. And it operated from 30 to 3,000 megahertz, or gigahertz. You cannot build a shield to cover that range even. It's impossible. There's no such animal. So they build this shield. It's basically radio frequencies and thermal, but does not include microwaves. Here's its orbit. Here it is here. What's the altitude? 900 kilometers. That's not very far. And the Earth is what? Covered in water. And the atmosphere is covered in water. So there's lots of microwaves coming here. And it has a shield that can't block microwaves. So all the microwaves are coming up from under the Earth, under the satellite. They go up there, they diffract in, and they're getting microwaves from Earth. There's no way they can stop it, right? But they think they measured the temperature of the universe. They actually measured what? Microwaves from water from the Earth. But they think it's cosmic. Here's how it works. Now, the FIRIS is an absolute instrument. This is a bit of a misnomer because it's a comparator. But they call it an absolute one because the sky is compared not to the sky, but to a calibrator. They put on board a calibrator and it's a black body. They made themselves a black body, a Kirchoff black body. They lined the thing with black stuff and it gets a nice black body curve. And so the idea is take the sky signal and plug it in there and take the signal from your calibrator. You can vary the temperature a little bit of your calibrator and you plug it in there and then you take the difference between the two. And if you get 0, you know that the sky matches this. So you can say, the sky has the same temperature and nature as the calibrator. This is black body, and we set it at a temperature. They set it, they say they got a temperature of 2.725 Kelvin. But, the thing is, if and where the sky matches the onboard calibrator, they call it a null, or 0. If it's a difference of 0, it's a null, or 0. A 0 should occur in the interferogram. What's an interferogram? It's the map of the difference between the sky and the calibrator. Let's have a look at one. Here it is. The Kobe FIRIS team produces this graph. They say, look at this. The internal reference, that's the calibrator, is set at 2.759 Kelvin. And the sky data is near null. Oh, yeah, it's a nice, there's very little bit there. This is all nice and smooth. And yeah, we've got this. Here's the internal calibrator at 2.771. Sky data goes in and it's off null. Yeah, well, it doesn't match that one. They say it seems to match this one. And look at this. There's a big chunk. There's a big blip here. And here they've got 2 calibrators, one internal and external. They compare the two. Yeah, there's a big blip. They couldn't get the 2 calibrators to match. Well, did they get a null or 0 anywhere? The answer is no. See this one here and this one here? The amplitudes of these 2 graphs have had have been suppressed by a factor of between 3 and 5. So this one here and this one here do not match the scale here. Do they tell you that in their graph? No. How do you know that? You have to be an expert in imaging science to spot it. Who did it? Professor Pierre-Marie Robitaille did that. This comes from Mather and his colleagues. Mather was the principal scientist on the Kobe FIRIS. So we see that this and this are not on the same scale as that. If you amplify this 3 to 5 times, is that flat? No way. Did they get a null? No way. And they reported a temperature of what? 2.725. Here they say they got a near null at 2.759, but they didn't get a null at all because this and this are not on the same scales. Right? In 1990, they first reported that they were taking samples between 1 and 2 centimetres to the -1. This is effectively their wavelengths, right? 1 centimetre down to 0.5 millimetres. But after 1990, they stopped reporting. After that report, they stopped reporting all data less than 2 centimetres to the -1. Well, you know, we were talking about the satellite and the diffraction over the shield. The lowest frequencies are the ones that diffract the most. An acoustic engineer will tell you that too. The lowest frequencies of sound are the ones that diffract the most. So they dump that. Why? They're the ones that are very important because they'll really tell you if you've got diffraction. But they decided, we don't like that data, we'll throw it away. As I said, it's the lower frequencies that do this. Now, everything else that didn't fit their curve, they threw into a thing called the calibration file. Oh, that doesn't fit. We'll calibrate that. So I put it in there. This doesn't fit. We'll calibrate that. So they got rid of this data. Then they calibrate everything else, and they get themselves a perfect curve, which they say is this. It matches the Planck black body curve at 2.725 Kelvin perfectly. So much so that the thickness of this line is 400 times greater than our error bars. You know, you have to expand this 400 times to be able to see their little error bar. That's how accurate they say this matches the theory. Where's the data less than 2 centimetres to the -1? It's not there. Is this labelled properly? Let's count. 1, 2, 3, 4. Is this labelled properly? No. This is advertising executives at work. You produce a graph, you put in this sort of thing, you don't say anything about it, people look at it and say, isn't that marvellous? But it's deceptive. Bearing in mind the interferogram, how did they get this perfect curve? And remember, we've already seen that Planck's law and Kirchoff's law are invalid. So you can't get a black body curve from anything but a solid. How did they get this from space? They didn't. So this graph is totally meaningless for the cosmology. The universe is not in a cavity. So you can't even use thermal emission theory because it all comes from radiation from a cavity. Is the universe in a cavity? Is it in a box? No. You reckon it is in a box? I beg to differ. Here is how the Kobe differential microwave radiometers work. Now, the DMR was a differential instrument. What does that mean? It means you take the sky signal from one antenna and you stick it in here. Then you take the sky from another antenna and you stick it in here. Then you take the difference, and anything that's isotropic, like the monopole signal, right? That's the same everywhere. So it will be the same here and the same here. Now, if you subtract something from itself, what do you get? 0. So if the monopole goes in there and the monopole goes in there, you have no chance of detecting the monopole, because when you take the difference, the monopole drops out. And all you're left with is little bits that are different in these two channels. And they're called anisotropies. This is how you get maps of the so-called anisotropies, or the little variations in the cosmic microwave background, by using this kind of thing, a differential instrument. Here is an artist's impression of the monopole signal. This is the whole sky. Well, it's an oval, but that's how the WMAP team and Planck present it, so I do the same. And this is an artist's impression because I drew it. And you see here, everything's nice and smooth. If I take this away from itself, what do I get? 0. That's the monopole signal. It's isotropic. And you can subtract that. Yeah, we saw how you can do that. You just put the signals into the comparator and you take them all apart. Now, here's the dipole signal. This comes from the Kobe team. This dipole signal we mentioned before is due to the motion of the satellite against the galaxy, against the galactic group rather, local group. And this varies in time and it varies in direction. So they take a snapshot. Here's one example of the dipole. It changes all the time. Here is one. And when you take a snapshot and we want to get rid of that, the dipole signal is anisotropic. So you can't subtract that out, can you? No. You can't get rid of that. If you subtract signals, you will get this bit left. So how do you get rid of it? You data process it with computers. Here is the map from Smoot, who was a principal scientist on the Kobe DMR. Notice this big band here. What do we recognise that as? Well, that's the galactic foreground. Why is it present? Well, it's a big anisotropy. He can't get rid of it because you're all looking through the galaxy. There's a lot of radiation there. This is microwave, right? But this is the anisotropic. So he's data processed out the dipole signal we just looked at. The monopole disappeared because he subtracted it with his instrument, differential instrument. So you're left with anisotropies. But the galactic foreground is a big anisotropy. And how do you get rid of that? Well, you have to data process that out because the galactic foreground can't be removed. So he gets an anisotropy map. He can't get rid of the foreground. This is a big problem with all of these satellites. So he gives you a map. All of these are the wrinkles in space-time. He calls this the wrinkles in the fabric of time. All of these little things here. And this one here, what would be behind that if you could get rid of it, if this is true? Would you expect more little green and blues and white, yellows and things? Yeah. You would expect that. If you could get rid of this, behind all it, you'd have all of this stuff filling the sky, wouldn't you? You would expect that. Yeah? Well, if you can't data process it out, how do you get rid of it? Well, you can use scissors or Photoshop. Here we have another. Well, where's the foreground gone? This is not I didn't do this. This came from the scientists. Here you got the anisotropies here. What's this? Did you use scissors or Photoshop? One or the other. So this is what? All this stuff that's supposed to be in here, and you tell us that this is the galactic foreground subtracted. Well, that's not subtracted. That's just nothing. And as I said, he calls this stuff the wrinkles in the fabric of time. Well, here's a really interesting thing. I'll read this out. I have to read this out. This is Smoot. We were confident that the quadrupole... Oh, that's what I should have mentioned to you. He couldn't get the foreground. He couldn't get his anisotropies. He scratched his head. He got rid of the dipole. He got rid of the monopole. He couldn't get rid of the foreground. But he says to himself, the anisotropies should appear now. I've got rid of these two noisy things, other than the foreground. He scratches his head. He says he couldn't figure it out. Why? Well, then he went to the quadrupole. Remember the slides I gave you? It's one behind. It's one behind the dipole. He says, I should have my anisotropy. So he says, we were confident that the quadrupole was real. That's the one behind the dipole. By late January and early February, the results were beginning to gel, but they still did not quite make sense. I tried all kinds of different approaches, plotting data in every format I could think of, including upside down and backwards, just to try a new perspective and hoping for a breakthrough. Then I thought, why not throw out the quadrupole, the thing I'd been searching for all those years, and see if nature put anything else there? Why, I puzzled, did I have to remove the quadrupole to see the wrinkles? So their own theory was telling them, take out the foreground. We couldn't do that. Take out the monopole. Yeah, we can do that. Take out the dipole. Well, we processed that one out. And now nothing's there. We'll remove the quadrupole. And what does he get? All of these anisotropies. Marvellous. We found all the little wrinkles in space-time. What does Robitaille tell us? He analysed all this. What does he tell us? Robitaille's an expert in imaging science. He says this. The answer to this question is one of data processing. When Smoot and his colleagues imposed a systematic removal of signal, they produced a systematic remnant. In essence, the act of removing the quadrupole created the multipoles and the associated systematic anisotropy. Once the quadrupole was removed, the multipoles appear as extremely consistent variations on the maps. And Robitaille adds that apparent anisotropy must not be generated by processing. So in other words, Smoot and his colleagues could not tell the difference between data and data processed spots before their eyes. This is all produced by what? Their data processing. We know in many other areas of imaging science that data processing will produce ghost images. They're not there. He couldn't tell the difference between it. Now, here is L2, the WMAP and Planck satellites. They're orbiting Earth. They're here. Here's L2. This is where Planck and WMAP were located. L2 is how far away? 1.5 million kilometres from Earth. There it is. Yeah? And there's Earth. So it's further away from the sun than Earth. That's L2. Yeah? Here is how WMAP worked. It's a differential instrument. Remember we put up a simpler diagram? Well, here it is, one of their own diagrams with all their electronic gizmos. Sky goes in here. That's a comparator. It spits out something. The difference between the two. That's how they design their radiometer. Same thing as what I said. Now, here's their maps. They sampled at 5 different frequencies. Look at this one. See all that red stuff? That's the galactic foreground. That's pretty dirty. This one too, this one too. This one, these two here have got a lot of noise in them too, but they don't like this one. They don't like that or that either. So what do? Well, the first thing is they have to make a single map out of all of these 5 frequencies. So they superpose them all in a way. And they arbitrarily decide on what weights they'll lend to each of these maps. And what do they decide to do? I don't like that one. I don't like that one either. So they decided, let's go for this one. And so they gave this prominence. And they downplayed all of these. You know? This is mapping by trickery. Then they get this beautiful map. Where's the foreground? They've got rid of it. How do they do it? By data processing. All of these things here, they're the anisotropies. The same things that Smoot got. This is WMAP. What's the alleged signal strength? Well, all of this is microkelvin. That's 1/1,000,000th of a Kelvin, right? So it's in microkelvins, microkelvin. But what's the galactic foreground? The galactic foreground is in Millikelvin, it's 1,000 times stronger. So we know something about this. If you have a signal that is 1,000 times weaker than the noise, we know from laboratory experience that you cannot remove the noise unless you have one of two options. One, you have a priori knowledge of the nature of the source, or two, you can physically manipulate the source. If you can't do either one of them, you can't get rid of that noise. It's impossible. They say they did it. Well, they did better than any radiometric laboratory in the world can do. With this satellite, they say. That's not a chance. Here's the Planck receiver chain. The sky goes in, and they use as kind of like Furus. They compare, remember Furus had a calibrator on board. This one has a load, a reference load, a 4K black body. There's two of them. Planck carried two 4K reference loads. There were two kind of detectors, the low frequency instrument and the high frequency instrument. I'll only talk about the low frequency instrument because once we've done that, it's all over. So they take the sky, they put it in here, and they compare it to their 4K reference. That's emitting black body. They made a black body out of black stuff in a box. Then they compare them, they take the difference and they play around with it and they say, well, we got all these anisotropies like WMAP. Let's have a look at their black body comparator. Well, how do you feed the radiation from your black body into the comparator? Well, you have to have a horn to collect it. Just like their antenna or their horn collects from the sky. You've got a big horn, comes in. Well, they use this one. They've got a horn here, and the radiation's supposed to come off here. It's supposed to be around about 4K, and it's supposed to be black body, because all of this stuff's black. Yeah? So if you've got radiation going into here, you can take that off and stick it into your comparator and compare it to the sky up here somewhere and spit out the answer. Right? Let's have a look at this. Here's your black body reference material inside here, your reference horn. This thing here is an aluminium casing. Yeah? And this here, well, they had a problem. They couldn't keep the black body at 4K because they didn't have any convenient cooling method. So what did they decide to do? Well, the high frequency instrument had a shield. And so the high frequency instrument was kept at 4K as well. So they decided, well, we'll keep it at 4K, easy. We'll bolt this against the high frequency shield. That's at 4K. That will keep us in thermal equilibrium and we'll have a 4K box. Yeah, great. So they did that. The trouble is, see these paths here? They did that with steel washers and they put in screws. That's metal. What does that do? That creates a conduction path. Now you have conduction from the black body. This is no longer a black body. Why? Because it cannot emit photons. In fact, it doesn't even have to emit a single photon. All the energy to keep this at temperature can be drained into the shield by conduction. This is not a black body. Both of their black bodies are mounted like this, so they have no black bodies on board. They are effectively getting zero from here, which means that they are getting zero into their horn here and comparing to the sky. And what did they report? We got a really good result. The reason why? They're comparing zero from here to zero from the sky. That's why they got a good match, which means there is no monopole signal. That means there's no cosmic microwave background at L2. This proves it, and they don't even understand that that proves it, and they don't even realize that they've stuffed up because conduction ruins this. Now, that comes straight from the papers, the design papers by the Planck team. I didn't make this up. So they have none. So we're getting close to the end. Without the 4K reference loads, Planck has actually confirmed that there's no monopole at L2. Why is that again? Because their black body is not emitting photons. It's not black body. That means they're getting effectively a 0K signal. There's no signal. Then they compare it to the sky. They get a really good, nice match. Why? Because the sky must be at zero. If they didn't have that, if the sky was at some higher temperature, they would have a really huge offset in their device. They could tell straight away the power levels would go up. They didn't get that. So the only possibility is, since their black bodies are not black bodies, they are comparing 0 to 0. They have proven, without realizing it, that they have no monopole at L2. That means this cosmic microwave background measured by COBE is not cosmic. It comes from water on the Earth It's got nothing to do with the universe. It's Earth. And they can't get a black body curve because Kirchoff's law is now invalid and space doesn't emit in black body. Gases don't emit. They emit in bands. Gases absorb and emit in bands. You will not get a continuous spectrum from a gas or from space, right? So there is no cosmic microwave background. That's the history of the Big Bang. Well, we've already seen that general relativity can't manage more than one mass. We've seen that the equations that they compare for black holes and Big Bangs are incompatible. And we've seen that when the energy momentum tensor in Einstein's field equations is zero, there's no matter. He has no set of equations that mean anything. So it's the end of general relativity, and it's also the end of the Big Bang, right? Now, here's an interesting thing. It's now claimed that the axis of evil, I don't know if you've heard of it, George Bush once said about the axis of evil, that's a different one. Yeah. Bush doesn't know any science, of course. I don't think he even knows English. Anyhow, the axis of evil. It's claimed that the quadrupole, remember Smoot had to remove the quadrupole because he was wondering why he doesn't get inside isotropes. Well, the quadrupole and the octopole of the alleged CMB, the octopole is behind the quadrupole, and then the hexadecapole is behind that one. They say, well, we have a definite alignment with one another, with the ecliptic plane, the dipole, and the equinoxes, so that the Earth is the center of the universe. I'm not kidding you. They're telling us now that we're going back to a geocentric universe. The Earth is not just at the center of the solar system. They're using the CMB to tell us that the Earth is at the center of the universe. Well, really? And what shape is the universe, since it's got a center? Microwave radiation from Earth has nothing to do with cosmology. Cosmology is not even a science, you know, and we do not live in a geocentric universe at all. Thank you very much.